Hi everyone, my name is Marianna and I'm going to tell you about the work I did with my advisor, Andre Lhoták, on generalizing the dot calculus to support fully path-dependent types. We're all familiar with the tragedy of Romeo and Juliet and the hatred between their families. But the real tragedy would have been if Romeo and Juliet actually got to get married, because then we would have to organize their wedding and we will have to come up with seating arrangements for the guests while ensuring that no Capulet sits next to a Montague. And of course, if they had Scala and path-dependent types, this would have been easy. So what they could do is they could create this abstract class family, and family will have a type member called family member. And so just like a lot of object-oriented languages allow objects to have members that store values, in Scala, objects can store members that are types. So now what I can do next is create a class table separately for each family, and I will have a method that will seat a guest of that specific family at the table. Okay, so now I can create a Capulet family, and to do that I instantiate this type member, family member, to the Capulet type, and I do the same for the Montague family. And now if I have a Lord Capulet and I have Lady Montague, and I also have a Capulet table, I can seat Lord Capulet at the table without problem. That will be fine. But if I try to seat Lady Montague at the table, I will get a type error at compile time. And the reason that this happens is that my seatGuest method takes an argument whose type depends on the object, on the family object. Okay, so a Capulet table will not go well with a Montague family member. And so path-dependent types is really the feature that allows us to do this. So more generally, a path-dependent type is a restricted form of a dependent type that depends on the runtime value of a path to an object. So, and by path, I just mean something that starts with a variable and has a finite number of fields, or maybe 0 fields on it. Okay, so in fact, after a decade of search for a sound formalization, that formalization appeared only in the last couple of years in a calculus called DOT, which stands for dependent object types. And so DOT formalizes these path-dependent types, which is just a way of referencing abstract type members that Scala can have. And so both DOT and Scala allow these type members to be declared with custom lower and upper subtyping bounds. And this is what makes this feature really tricky, but also really expressive. Furthermore, values and types in DOT can reference the self or this variable of the enclosing object, for which it uses recursive types and recursive objects. And then it models intersection and, it models mixing composition and inheritance through type intersection. And finally, DOT has unique top and bottom subtyping bounds, that model any and nothing in Scala. Okay, and now, so together, this small number of features yields a surprisingly expressive type system that allows us to model not just Scala, but a lot of important concepts in other programming languages. For example, family polymorphism, which we just saw, but also parametric polymorphism and a number of other features from Scala and other languages. And additionally, DOT also serves as the theoretical foundation for the next version of Scala. Okay, that's nice, but it turns out that DOT doesn't actually model path-dependent types, but only variable-dependent types, which must have a path of length 1. Well, now, does this limit the expressivity of the language? Well, let's see. So suppose I have Lady Montague, which is a field of this path-dependent type. So this, you can see, is just a variable-dependent type, so that's fine. But as soon as my type member moves into a nested package, now in order to access it, I actually need a path of length 2. Does that make sense to you? Yeah. Okay, so well, you might think, well, just move that field out of that object and make it a local variable that is fully defined outside of the object, because now you can have a variable-dependent type on it. But the problem is yeah, you can do it in this case, but if you want to have any kind of recursive references between your modules, you won't be able to do that. And nesting and recursion are features of real-world programs. For example, here is a simplified excerpt from the Scala compiler, and it shows that in order to represent all the complicated dependencies between the nested modules that recursively reference each other, you really need path-dependent types of length greater than 1. So if we only allow path-dependent types on variables, then this limits the expressivity of everything that deals with modules and classes. So it doesn't faithfully model these features. And so at OOPSLA 2016, we got together with Martin Odersky to discuss how we can solve this problem. And at the time, it really seemed like it would be just a simple syntactic change where we generalize variables to paths and everything would be fine. But trying to do that opened up soundness holes at every step of the way, which is why it took us over 2 years and 3 attempts to do this. And so the rest of this talk is going to be about identifying these soundness holes and finding ways to patch them while maintaining soundness and expressiveness of the language, which we call PDOT. So to start off, it would be nice to know, well, what does Scala do to make path-dependent types work? And what Scala does is that it says paths that participate in path-dependent types must be stable, which means that all the fields that are part of the path must be immutable. So if I have an object and I have a field v, and v is something that has this type member, family member, then I can invoke a path selection on it. I can have a path-dependent type. That path is stable. That's fine. But if I have a method, f, that has the same type, then it has been shown to be unsound to have a path-dependent type on it because essentially methods can evaluate to objects of different types every time that they are called. So that would be unsound. So if we want to have path-dependent types, we need to be able to distinguish, just another note. So here's how we would represent this in dot. You can see it looks really similar. And in particular, you can see that methods and fields are modeled in exactly the same way, so we don't distinguish between them. And moreover, these so-called term members evaluate each time when they are called. So they correspond more closely to methods in Scala. So yeah, so if we want to, and this means that we can't have path-dependent types on them. So if we want to have path-dependent types, we need to be able to also model fields, but distinguish them from methods. And so what we know about fields is that they evaluate at object creation time. So by the time that we call this field v, the right-hand side will be fully evaluated to a value. And so in PDOT, we need to do the same. We need to make sure that the right-hand sides of values of fields are fully evaluated values, which can be functions or objects. So if a right-hand side is an object, then I might be able to have a path-dependent type on them. But I also want to be able to model methods. And I do that by explicitly delaying the computation of the right-hand side by wrapping it inside of a lambda. And if I do that now, I will also have to adjust the type of this field to a function type. And of course, it wouldn't type check to have a path-dependent type on a function. And this is good because I don't want to have path-dependent types on methods. But now this might seem a little bit restrictive because now I only allow values on my right-hand side. So I also want to be able to have paths. But now we run into a different problem. So in an object, we assign a type to each field. And this type serves two purposes. So the first one is that it provides information about the field outside of the object. And just a quick note on syntax. So this means that the term x.a has type t, assuming the typing environment gamma. So now, besides providing information, the type t also provides assumptions about the object within it. So what that means is that when I type check the object and I check that all the fields have the right type, I don't just do it just like that. I do it in an extended environment that assumes that x already has this type. And I need to do that to support recursive references. So this means now that if my type introduces nonsensical assumptions about the object, and I can type check the object, then this nonsense can propagate outside of the object, causing unsoundness. Now, the way that this can work is if I have cycles in my field references. So for example, here, you can see that the field A references itself. So it's a cycle. And now if I type check it, is that if I type it with this type declaration B, now, of course, assuming that X has this type declaration type, of course, X.A will have the same type. So now I bring this outside of my object. And what do I have now? Well, I have this lower bound top. So that must be a subtype of B. And my upper bound is bottom. So bottom must be a supertype of B. I also know that any type is a subtype of top. And any type is a supertype of bottom. So then, because subtyping is transitive, I get that any type is a subtype of any other type. So types completely lose their meanings because I can't type any value with any. They don't tell me anything about values anymore. Now you might think, well, just don't allow this nonsensical type in the first place. But previous work argues that it is in general impossible to rule out these so-called bad bounds without losing, while maintaining expressivity of the language. So it turns out that dot actually has a very similar problem. So, but only when it comes to top-level type declarations. And the reason is that variable-dependent types can reach into the top-level declaration of an object, and that would cause unsoundness. And that's why in dot, we don't allow these arbitrary type bounds at the top level. We say that these type bounds must be equal. And then we will not get this unsoundness. But we don't care what happens deeply inside the object because no path-dependent type will ever be able to reach there. But that's exactly what we want. We want to have these arbitrary length paths that can reach inside of objects. And having it just like that would be unsound, which is why we require type bounds deeply inside of objects also to be equal. Well, just like dot requires them to be equal at the top level. But it turns out that this is not enough. Even if I don't even if I don't type my field with a type declaration, but let's say just with a record type, C, I also get a problem. And that is because according to this type of this object, x.a.c is a valid path that has some type. But notice that x.a doesn't have a field called c. And so x.a.c doesn't reduce to anything. And now I have that something that has a type doesn't reduce to anything and is not a value. And that's the definition of unsoundness. So what I need to do is have some more precise information about this field and my type. And what I require then is for object fields to have precise types. So if my field is a lambda, then it must be typed with a function type. If it's an object, it must be typed with a recursive object type. And if it's a path, well, there's not really an obvious type for a path because I don't know what this path points to. And this is where singleton types come in. So a singleton type, p.type, is a type that is inhabited by exactly one value, namely p. And I require my field that is equal to a path to be typed with a corresponding singleton type. And so here, this tells the type system that the path x.c is equal to y, points to the same object as y.d. And therefore, I will be able to type check x.c with any of y.d's types. Now, you might wonder, well, what if I have a cycle? Well, if I have a cycle, that's not a problem anymore because x.c can only be typed with x.c.type, and it can't be typed with any other type that could cause bad bounds. Okay, that looks nice, but it seems also a little bit restrictive because Scala allows us to program with abstractions, right? And we require these precise types. And our response to this is that the place for abstractions is not in the assumptions about fields. It's outside of objects, because objects just prove that an abstraction eventually makes sense. And so specifically the way this works is that if I have an object x and it has this precise type t, I can still ascribe a more abstract type u to it by just passing x through an identity function that accepts type u, something of type u. And now the nice thing is that the type of this whole expression will be u rather than t. So just to give you a more concrete example, if I start off with this previous super precise type, I can now do something more abstract with it. So for example, for field A, rather than using a function type, I can use this path-dependent type. And rather than using this field B, maybe I just want to leave it out completely. For field C, rather than using the singleton type, maybe I will use a record type as long as y.d has this record type. And then for my recursive type, I'm going to just get rid of the recursion and widen my type bounds. OK. So now we have abstractions, and that's nice, but turns out that this is still unsound. And the reason is that if I have a path that points to some object, let's say it has some field A, it doesn't really matter, and now I'm typing this path with a corresponding type. It will be a recursive object type that also has this field. So notice that I'm using this variable x to represent the self or this variable of this object. And so this obviously points to the object itself, but also p points to the object itself. So they point to the same thing, so I ought to be able to get rid of this recursion and replace x with p, because they are the same thing. But now, so soundness says that if p has some type and p reduces to something, then that something should have the same type as p, right? But notice also that this object doesn't have anything to do with p anymore. So it doesn't have this type. OK, so what does dot do in this case? Well, it actually has a similar problem, just for variables. And the way it addresses it is that it says, well, variables represent object identity. So we don't reduce variables. And so since p dot generalizes variables to paths, then in p dot, paths represent object identity, and so we don't reduce them. But then you might think, OK, if I have a program and it reduces to, it evaluates to a path, and I don't reduce this path anymore, then what does that mean? I mean, what do I get out of this? What does this path mean? And what we proved in our type safety proof is that if a path has a type, then you can look up this path in the runtime environment, and it will map to a value of sort of almost a type t. Or if not, then it must be participating in a cycle. But that will only happen if t is a singleton type. And so well-typed paths don't go wrong. So to summarize, p dot generalizes dot's variable-dependent types to the first formalization of fully path-dependent types and singleton types. And this allows us to model a variety of features of an expressive type system such as scalas, and to unleash the full expressive power of path-dependent types. Thanks.
So thank you very much for the nice talk. I think we should have more talks with Shakespeare references. So my first question is, so how exactly did you find out about the unsoundness in the original version of dot? And also, I would like to know which kind of formal methods did you use to prove soundness? Did you use the normal progress and preservation proofs or something else?
Right. So, I mean, I think the general unsoundness that, you want to have paths that evaluate to something, and so they might not terminate, and you want to have a type selection on something that might not terminate. It was obvious that this is unsound. And we had some ideas of trying to rule out cycles and paths, but it just didn't lead us anywhere. And so these soundness issues, most of the soundness issues that I showed to you were, painfully found after years of working on this and almost finishing the proof, and then finding that last little thing that doesn't work. And then the second question was what we use. Yeah, we used progress and preservation, and we implemented this type safety proof in Coq, and it's an extension of the simple soundness proof of DOT that we presented at Uppsala 2 years ago. I can tell you more about that if you want. Yeah, thanks.
All right, so Scala has defs and vals, but it also has vars. Will anything go wrong if we add in vars to your calculus?
So you mean mutable variables?
Mutable variables.
Yeah. So even in Scala, you are not allowed to have path-dependent types on mutable variables. So that's very easy to rule out. Another similar question might be about lazy vals, which I didn't mention. So lazy vals are basically fields that are not instantiated at object creation time, but are instantiated lazily when they're called. So they're a little bit similar to defs. And they're allowed in Scala. And so, different versions of the Scala compiler have employed different heuristics to make reduce the number of cases in which path-dependent types on lazy vals are unsound. But we have something that is, provably sound. So.
Really nice work.
Thanks.
So a related question to the lazy vals maybe
Okay.
is defs, right?
Right.
Because I believe earlier versions of DOT are actually purely functional.
Yeah.
So a def, I would guess maybe a def without any parameters or the same parameters at each call site should actually return the same thing every time. Is this something that is there a reason that would be unsound?
That's a good question. So
to actually use
Right.
pure functions in a path, or is that just something that wasn't in the
Right.
scope of your current proof effort?
Yeah. So do I understand the question that the reason that defs are unsound in Scala is that they are unsound in the presence of mutation? Is that what you meant? Yeah, you're absolutely right. It's a good point. But they are also unsound because they might not terminate. And the difference with fields is that by the time that the evaluation context reaches a field, it's already fully evaluated to a value. So if that was non-terminating, we wouldn't even get to that point in the context. Does that make sense? Does that answer the question?
Yes, but normally we don't require non-termination to prove soundness, right? Unterminating programs are usually sound.
Absolutely, and we can totally have non-termination in PDOT as well. But you don't want to have a type selection on something that doesn't terminate, because you could have typed the non-terminating thing on something with an arbitrary type, and that could give you unsoundness. Or if that doesn't answer, maybe we can talk more.
Thanks.
Yeah.
Maybe one last question?
Yeah.
So thank you very much. This is really exciting work. I'm super thrilled to see the new results coming out.
Thank you.
So I have one question though, and that relates to kind of the power to weight ratio of.
Sorry, the what ratio?
The power to weight ratio, so
Okay.
the power to complexity ratio.
Okay.
Right? So, and I'm just wondering, and maybe this is a discussion to talk about offline, but sort of with these paths that can be recursive, right? Is the extra expressiveness really worth the complexity? And wouldn't things be much simpler if you just said, okay, the right hand side of val defs can only be object initializations, basically?
Can only be?
Can only be object initialization. So you can have a
Right.
new object, you can have a lambda, but that's it basically.
Yeah, I mean, I think it's just nice to also be able to have paths, especially if we say that, we already require the right-hand sides to only be values. So if there's no cycle, we sort of know that a path will not be, nothing bad will happen. So it's really, and this is also, of course, something that you want to be able to do in Scala. I think it's a more philosophical question of any of this complexity, even without paths, is worth it, right? Yeah.
Thanks.
Yeah.
Okay, let's take this